Okay, so before we start lesson 4, I'm just pulled up the syllabus calendar. This is in your syllabus. So I just want to explain a little bit more how it works. So we've got the day and the date here, and then the lessons covered. These are the lesson numbers from the packet, right? So Tuesday we did 1 and 2. Today we did all of 3, meaning the lecture part and the activities part. And then we're going to start 4, which means just the lecture part. And then when I see you again on Tuesday, we'll finish 4, which means when you come in, you'll immediately just do the activities for 4, and then we'll do all of 5, the lecture and the activities. So that's sort of how I took 3 lessons in a week into 2 lessons in a week. It's either lecture, activities, lecture, or activities, lecture, activities. And then just to point out that Thursday, I'm sorry, not next week, but the following week on Tuesday is your first quiz. And so that's going to be finish 7, which means we'll do the activities for class 7, and then we'll take a quiz. All right. The 3 worksheets. I'm going to come around and check them as homework next week. All right, so we're going to go to class 4. I'm going to do the lecture part from class 4, the demo part, and then the activities we'll do next class. So we're not going to get to the activities today. Don't feel like you need to finish them outside of class. All right, so we're going to talk about vector equations. We're going to learn about linear combinations of vectors, how a linear combination of vectors is related to a system of linear equations, and a key concept that we're going to focus on is the span of a set of vectors. All right, so I've got 2 vectors here, u and v. U is 1, 0, 0, v is 0, 0, 1. If I want to compute 3u plus 4v, when you multiply a vector by a scalar, how do you do that? Yeah, every entry, one at a time. So you multiply every entry in u by the scalar 3. So this is 3 times 1, 0, 0 plus 4 times 0, 0, 1. And you just multiply every entry in the vector by the scalar. So this becomes 3, 0, 0 plus 0, 0, 4. And then how do you add vectors together? X's with X's, Y's with Y's, etc. Yes, you add them component-wise. So we end up with 3, 0, 4 when you add them together. 3u plus 4v, what is that expression called? A blankety blank of u and v. Nope. A linear combination, right? From your reading. Right. Give another example of a linear combination of u and v. You want me to come up with one? Okay. Oh, yeah, that's how you do vector arithmetic, right? Yeah. Has to be addition. Yeah. You can put scalar weights on the vectors and then you add them together. That's what a linear combination is. Yeah. So all you need to do is pick 2 scalar weights. Somebody throw out 2 numbers for me. 0 and 0. Okay. So if my weights are 0 and 0, then a linear combination would be 0u plus 0v. You just pick any 2 random scalars, you multiply them times the vectors, add them together. That's the definition of a linear combination. So in this case, my result would be 0, 0, 0. Good. So there are infinite linear combinations you can make, because there are infinite choices for scalar weights, right? So if I wanted to talk about all of the possible linear combinations of u and v, what's the special name for that from your reading?
That would be the span.
The span, yep. It's the span of the two vectors u and v. Now, in your textbook, when they talk about, when they are using vectors, their notation for when they're talking about vectors is they make the letter bold, right? When I write on the board, just because it's like, I don't want to copy over my letter 15 times to make it look bold, I put a little arrow over the letter to mean that it's a vector. So the span of u and v, that means all the linear combinations of u and v. And again, linear combination is just scalar multiple of each vector added together. Give another example of a vector in the span of u and v. So we have 2 so far. We've got 3, 0, 4 because that's a linear combination, so it's in the span. We've got 0, 0, 0. That's a linear combination of u and v, so it's in the span. What's another one? 12, 0, 7, because that would be 12u plus 7v, 12, 0, 7. That's a vector in the span of u and v. If I want to describe all of the elements in the span, I want to describe the span of u and v using set builder notation, which we talked about Tuesday. What do all, let's just think about it in terms of words before we go to set builder notation. What do all the vectors in the span of u and v look like? Or what do they all have in common? The 0 in the middle entry, right? Do the first and second entries have to have any relationship to each other? No. Okay, so my span is going to look like the set of all 3 entry vectors. First and third can be anything, so I'll just write A and B as placeholders. But you have to have a 0 in the middle entry. So it's all vectors that look like A, 0, B, such that A and B are elements of what? Not Z, bigger, R. Yeah. Yep. The definition of a linear combination is that those scalar weights that you can pick have to come from the real numbers. So linear combination means pick scalar weights from the real numbers, multiply them by your vectors, and add them together. How many elements are in the span? Infinite. They're infinite linear combinations because there are infinite real scalars that you could choose as the weights. So this is infinite. Is the span of a set of vectors always infinite? If my vectors weren't these particular u and v, right? Is there any way that you could make pick a set whose span is, yeah, if the only vector in your set is the 0 vector, then its span is just scalar multiples of the 0 vector, which will always be the 0 vector. So is the span always infinite? Almost always. There's the one exception where the span of the 0 vector will always give you the 0 vector. Is the 0 vector always, sometimes, or never in the span of a given set of vectors? Always. How do you know that? Yeah, so your weights that you choose to put on each vector, if you choose them all to be 0, like we did in part C, right? We were picking a linear combination of u and v, and somebody picked 0s as the 2 weights, right? You can always do that, so you'll always get 0 in your span. The span of a set of vectors always includes 0. All right, here are 3 questions that all mean the same thing. Is a given vector a linear combination of 2 other vectors? That is, can I find weights to put on these 2 that would give me this one? Make sense? All right. Exact same question with different wording. Is this 4, 12, 4? Is it in the span of those other 2 vectors? It's just another way of asking, is it a linear combination of the other 2 vectors? And then if I wanted to ask it geometrically, I could say, is 4, 12, 4 contained in the same plane as the other 2 vectors? And in your activities, I have you work with some geometric stuff. But basically, this question is saying, are there weights, right? So can I find a weight? Call that x1 maybe. Are there 2 weights, an x1 and x2, so that when I take a linear combination of those 2 vectors, are there 2 weights that I can find that will give me the third vector, 4, 12, 4? Can I find an x1 and x2 that will do that? You could just sort of guess and test in your head and see if you can find it. But let's just do a little bit of translating notation here, right? Remember, when you multiply a vector by a scalar, you multiply every entry by that scalar. So this says 2x1, x1, negative 3x1, plus 6x2, 5x2, negative 7x2, equals 4, 12, 4. And then when you add vectors, you add component-wise. So you add the first entries. That has to equal the first entry on the right. And then this says x1 plus 5x2 equals 12. And this says negative 3x1 minus 7x2 equals 4. System of equations, right? You can solve this by using a matrix, like what we've been doing for the past couple of classes. So I'm going to spare us the time of solving it using a matrix. I did it ahead of time. So I would just translate this to 2, 6, 4, 1, 5, 12, negative 3, negative 7, 4. And after 1, 2, 3, 4 different moves, I got it into RREF form, and I got 1, 3, 2, 0, 1, 5, 0, 0, 0. Oh, that's not RREF. You're right. That is close. I have one more move. I got to get rid of that 3, right? So I would multiply row 2 by negative 3 and add it to row 1. So this will become a 0. And then 5 times negative 3 is negative 15, plus the 2 that was there is negative 13. There we go. All right, now I'm done. Put it in our REF. So that says x1 is negative 13, x2 is 5. So what does that mean in terms of the original question, right? My original question is a yes or no question. Is 4, 12, 4 a linear combination of 2, 1, negative 3, and 6, 5, negative 7? Yes, yes. Because in our minds, we translate that question to say, are there weights that I can put on these 2 vectors to get the third vector? And the answer is yes, and I even found the 2 weights, right? If you have x1 be negative 13 and x2 be 5, then yeah, that is how we write it as a linear combination. So I would say yes, because, what was the vector? 4, 12, 4. 4, 12, 4 can be written as a linear combination of the other two, where my weight is -13 times 2, 1, -3 plus 5 times 6, 5, -7. Does that make sense? So you can do a quick check, right? -13 times 2 is 26, plus 5 times 6, so -26 plus 30 does give me the 4, the first entry. I can do a quick check. So that's it for the lecture part of lesson 4. Questions on it? Oh, I get that question all the time. That's a good question. I don't know. I don't know. Why aren't you taught this earlier in an engineering student's education? Because it's super useful to be able to solve multiple equations and multiple unknowns. Especially once I show you how to do it with your calculator. You're gonna wish you knew how to do it sooner. All right, so that's it. There's 8 minutes left, so if you want to go back to what you were working on before I stopped you,